So far we've discussed pH problems for strong acids and bases, so now we're going to concentrate on weak acids and bases. These problems are a little longer, a little more difficult because weak acids and bases do not ionize completely. And what that means is we can't determine our H3O plus or OH minus concentration just by looking at how much acid or how much base we put in, because not all of it's going to react. Instead, based on how much we put in, we can figure out how much H3O plus or OH minus we produce by solving an equilibrium problem. So these are almost identical to the problems we did in Chapter 14. We can write an equilibrium constant expression. For acids, we call this Ka. For bases, we call it Kb, but it's just an equilibrium constant expression. And we can solve an ice table equilibrium problem to figure out these equilibrium H3O plus or OH minus concentrations. Once we have those, we already know how to get from that number to a pH. So we already know the math for this. It's just slightly different terminology, a couple extra steps. And what's going to make life easy is we almost always use that x is small approximation. So that at least should help us out. So let's look at the general procedure for these. So when we're solving these equilibrium problems, the first thing we want to do is write a reaction of the acid or base with water. So that's one of these two reactions right here. So we have our generic acid equation, our generic base equation. And we should be able to write out the Ka or Kb expression for either one of them. So the first thing we do is write out that reaction. Then we write that expression for the equilibrium constant. And then we're always going to need to make an ice table. We can't solve these directly. So we're going to make an ice table. And here's where we have to be careful. This is one of my notes down here. We have to see, is the problem asking me for a Ka or a Kb, or is the problem asking me for a pH? These are the two different scenarios we might run into. So if you're given a pH and asked to find Ka or Kb, keep in mind that pH is actually telling you your H3O plus concentration at equilibrium. Or if you're dealing with a base, you can use that to find your OH minus concentration at equilibrium. So again, if you're asked for Ka or Kb, you should be provided with a pH, and just keep in mind that you can use that to give you the H3O plus or OH minus concentration at equilibrium. If, on the other hand, you're asked to find your pH, you're not going to have to use this piece of information right here because you won't have a pH to plug in. So we'll look at those two different scenarios. After you've plugged in everything you can to your ice table, you're just going to solve your equilibrium problem. So let's look at two examples. First example, a 0.1 molar weak base solution has a pH of 10.15. Find Kb for the base. All right, well, we know step one is always to write that equation. So we have a weak base. We don't know what it is. We'll just call him B. And we're going to react him with water. We use our double arrow because this is a weak base. Bases accept protons, so water will give one up. We'll generate BH plus. And as water gives off that hydrogen ion, it will produce OH minus. So first step, we have our equation. Second step we want to do is write our expression, this time for a Kb because we have a base. And we're just going to do our usual products over reactants. We don't have to worry about water because it's a liquid. Solids and liquids don't show up. So we have quite simply BH plus times OH minus over B. So we can't solve this right away. Obviously, we don't have any equilibrium concentrations. So now what we'll go ahead and do is generate our ice table. So we started with 0.1 molar of B and no products. So we have to add to the side with 0, and we'll take away from our reactant side. So at equilibrium, we'll have 0.100 minus X for B, and we'll have X for BH plus and OH minus. We can't really solve for anything right now, so we're just going to go ahead and plug that into my Kb expression. So on top I'll have X times X, or X squared for multiplying these two guys together. And on the bottom I will have 0.100 minus X. So it might feel like we're a little stuck right now. We're trying to solve Kb, but we still have an X here. But here's where we need to go back and remember, it gave me a pH. And if I have a pH, I can figure out an OH minus concentration. I know that these are related. So my pH is 10.15. Oops, let's scroll down, give us a little more room right here. There we go. So I know my pH is 10.15. So that means my pOH is going to be 14 minus 10.15, right? Because pH plus pOH gives me 14, so which is going to give me 3.85. So if I have pOH, I can turn that into an OH minus. OH minus is just 10 to the negative pOH, which is going to give me 10 to the negative 3.85, which, if I plug that into my calculator, gives me 1.41 times 10 to the negative 4. So now I have my OH minus concentration. So my OH minus concentration is given by 1.41 times 10 to the negative 4. And now I can see that that's really giving me X, because here my OH minus concentration at equilibrium is equal to X. So what I can do is I can go back to this expression and say, okay, if this is equal to X, now I can solve for this guy. So my Kb is equal to 1.41 times 10 to the negative 4 squared. So I'm just plugging in this value for X, because OH minus is equal to X at equilibrium, over 0.100 minus X, 1.41 times 10 to the negative 4. And if I plug that into my calculator, I'm going to get 2.00 times 10 to the negative 7. So remember, if it gives you a pH, you can use that to find either H3O plus, or in this case, because we had a base, we used it to find our OH minus concentration. That's going to give you your X at equilibrium, and then you can go ahead and plug it into your Kb expression and get an actual number down here. Alright, so that's one type of problem we can have. So this is where we were finding Ka or Kb. We are provided with a pH. We wrote our equation, wrote the expression for Kb, filled out our ice table, and then used the pH to get X and plug it back in. Now let's look at the scenario we're being asked to calculate a pH. So determine the pH of a 0.2 molar HCHO2 solution. And notice now we're provided with a Ka. Well, we're going to start this the same way. We're going to react it with water. Ooh, that's sloppy. Let's try that again. We have HCHO2 reacting with water. Double arrow because it's weak. We know he's weak because he's not strong. Another clue is that it gives me a Ka. Strong acids do not get a Ka, so I wouldn't have that for him. So an acid will donate a proton, so I'll be left with CHO2 minus, and that proton will join up with H2O to make H3O plus. Alright, so that was our first step. We wrote the equation. Now we're going to write the expression for Ka. As usual, we'll leave out water because it has a liquid. So we're going to have CHO2 minus times H3O plus over HCHO2. Getting a little sloppy there. So we're just doing our products over reactants. We do know Ka in this case, so we actually know this whole thing is equal to 1.8 times 10 to the negative 4. But that's about it. We don't have any of my equilibrium concentrations. So we can't solve for these guys straight away. We need to fill out our ice table. So my initial concentration of my acid was 0.200. I don't start with any products. I'm going to use up some of my acid. My equilibrium, I have 0.2 minus X. I'm going to make some of my products. It's all 1-to-1 ratio, so it's just X. So I'll have X and X at equilibrium. Okay, now that we filled out the equilibrium row, we're going to go ahead and plug it in down here. So let's free up a little more space here. I'm going to scroll down. Oops, not highlighter. Alright, so now we have this K expression. So, well, I don't know why this went away, but I had HCHO2 down here. There we go. So we're going to plug in my products. So that's going to be X times X, or X squared, over my reactants, which is 0.20 minus X. And that whole thing I know is equal to my Ka, which is 1.8 times 10 to the negative 4. So now I only have one unknown here. The only thing I don't know is x, so I can solve this equilibrium problem. But what I'm going to do for myself, since k is a very small number, I'm going to assume that x is also small, and I'm just going to ignore him right there. So this simplifies a lot. Now I have x squared over 0.200 is equal to 1.8 times 10 to the negative 4. So I want to get rid of this 0.2, so I'm going to multiply both sides by 0.200. So these will cancel here, and then to solve for x, I just need to take the square root. So I'm just combining a couple steps to be lazy here. So I'll plug this into my calculator, 1.8 times 10 to the negative 4 times 0.2, and then I take that square root, and that will give me x, which in this case is equal to 0.0060. So that x is small approximation is really handy. I do need to check it. I'm going to do my 5% check. So that's where we put x over our initial concentration. Make sure it's less than 5%. So I have 0.0060. My initial concentration was 0.200 times 100%. And if I do that, it gives me 3%, which is less than 5, so this approximation was fine. We're almost always going to be able to use this x is small approximation. So now I have x, and I have to ask myself, okay, what was I even solving for? Ooh, this is a mess. Let's go back and look. So I know now that x is equal to 0.0060, but what did I want? Okay, I wanted a pH. And now if I look, what I really care about is that x is equal to my H3O plus concentration. Now I see how I'm going to get my pH. So we scroll down and say, okay, x is equal to my H3O plus concentration. Now I see how I'm going to get the pH, because we know that pH is equal to negative log of H3O plus. So now my pH is equal to the negative log of 0.0060, and I plug that bad boy into my calculator, and I get 2.22. So now I have my final answer, my pH. So again, notice the difference between these two problems. In the first problem, we were asked to find, Ka or Kb. So we started the same way, wrote our reaction, wrote our expression for Kb, filled out our ice table, but we were able to use the pH to find that OH minus concentration and plug that directly into my Kb expression here. In the second problem, we were asked to find the pH. So we started the same way. We wrote my reaction, wrote the expression for Ka, filled out my ice table, plugged everything into my ice table, but now we were given Ka, so we had to solve for x kind of the long way. So we set them equal to each other, used x is small, solved for x, and then went back and recognized that x really gave me my H3O plus concentration, and because of that, we just had to take the negative log of that number to get my pH. Those are the two types of weak acid, weak base equilibrium problems we should be expected to solve.